Good evening all. Today we shall see the fourth module. Here we are studying electrical design of transmission line. In this session, we shall consider the inductance as well as capacitance of transmission lines. The resistance, inductance and capacitance are generally known as constants of transmission line. If we are considering a two-wire system, the resistances as well as inductances are coming in series with the transmission line, while the capacitance as well as conductance are occurring parallel to this conductor system. These resistance, inductance, capacitance as well as conductance are uniformly distributed throughout the length of the conductor. But for analysis purpose, we will consider them like this, as lumped as R1, R2, R3, etc. The performance of a transmission line is affected by inductance L, resistance R, and capacitance C. Then conductance also. The inductance is the most dominating line parameters. It is the inductive reactance which limits the transmission capacity of a line. The capacitance together with conductance forms the shunt admittance of a transmission line. Shunt conductance, which is mostly due to leakage over the surface of insulators, is almost always neglected in power transmission lines. The resistance of the transmission line causes the power loss in the transmission line. I squared R loss is caused by the resistance which is distributed along the total length of the line conductor. It is a deciding factor while calculating the transmission efficiency. So we shall see the inductance of a transmission line. It is a well-known fact that a current carrying conductor is surrounded by concentric circles of magnetic lines of force. In case of AC system, this field setup around the conductor is not constant, but changing and links with the same conductor as well as with other nearby conductors. Due to these flux linkages, the line possesses inductance, defined as the flux linkages per unit current. Thus, for determination of inductance of a circuit, determination of flux linkages is essential. So, inductance of a transmission line. The inductance of a circuit is defined as the flux linkages per unit current. It is expressed in Henry. L is given by N phi by I, or Li is equal to N phi, where N phi is called flux linkages denoted by lambda. The mutual inductance between two circuits is defined as the flux linkages one circuit per unit current in the other circuit. Thus, if current I2 produces lambda 12 flux linkages with circuit 1, the mutual inductance is given by M12 is equal to flux linkage lambda 12 divided by I2 Henry. Then flux linkages. So, in order to determine the inductance, we have to first determine the flux linkage. A long straight cylindrical conductor carrying current is surrounded by a magnetic field, as we have already seen. The magnetic lines of force will exist inside the conductor, which is known as internal flux, as well as outside the conductor, known as external flux. Both these fluxes contribute to the inductance of the conductor. So first we shall see flux linkage of a conductor due to internal flux. For that we shall consider a cross-section of the conductor. Consider a long straight cylindrical conductor of radius r meters. Let r be the radius of this conductor, which carries a current I amperes as shown in the diagram. In overhead lines, it may be assumed without appreciable error that the current is uniformly distributed. The magnetic field intensity at a point x meters, which is less than the radius from the center, is given by hx is equal to ix by 2 pi x. We know h is equal to Ni by L, where h is the magnetizing force or magnetic field intensity. It is equal to Ni by L. Here, the number of turns is 1. So, Ni by L here is equal to Ix by 2 pi x. For Ix equal to Hx into 2 pi x. Assuming a uniform current density, we have Ix by pi x square is equal to I by pi r square. Okay, the current at a distance x is equal to current at a distance r. So we can consider Ix equal to I, uniform current density. Or Ix equal to I into pi x square by pi r square. Substituting for Hx, we get Hx is equal to 1 by 2 pi x I into x square by r square, because pi and pi will get cancelled in this. So Hx becomes x divided by 2 pi r square times the current. That means ampere turns per meter. If mu is the permeability of a conductor, then the flux density at the considered point is given by Bx is equal to mu into Hx, where mu is equal to mu 0 mu r, absolute as well as relative permeability into Hx. That means Weber per meter square flux density. That is equal to mu 0 xi divided by 2 pi r square by substituting for Hx. As mu r is equal to 1, there will be only mu 0. Now, the flux through a cylindrical shell of radial thickness dx and axial length 1 meter is given by d phi is equal to bx into 1 into dx. That is equal to, substituting for bx, we will be getting mu 0 xi divided by 2 pi r square into dx Webers. This flux links with only the current lying within the circle of radius x, that is Ix or I into x square by r square. We know Ix equal to I into x square by r square. Therefore, the flux linkages of the shell d lambda is equal to x square by r square into d phi, that is equal to x square by r square into mu 0 xi by 2 pi r square into dx. Arranging the terms, we will get it as mu 0 I x cube divided by 2 pi r raised to 4 dx Weber terms. The total flux linkages from the center of the conductor and up to the surface of the conductor. This lambda internal is equal to integral 0 to r, that is the radius. D lambda. Substituting for d lambda, mu 0 I by 2 pi r raised to 4 is a constant. Integrating x cube dx within the limit 0 to r, we will be getting the answer as mu 0 I by 2 pi r raised to 4 into r raised to 4 by 4. Therefore, internal flux linkage is equal to mu 0 I by 8 pi Weber turns per meter. Now, flux linkage due to external flux. External flux is also created by the own current of conductor and extends from the surface to infinity. Let us again consider a cylindrical shell of radius x, where x is greater than r and with thickness dx. So consider the conductor with radius r and let its radius be extended up to infinity or up to x. Then consider a small portion of thickness dx also. The magnetic field intensity at the surface of the cylindrical shell Hx is equal to I by 2 pi x, as H is equal to Ni by L, N here is 1. So magnetic flux density at surface Bx is equal to mu 0 mu r Hx. Substituting for Hx, we will be getting, and mu r, taking mu r as 1, the expression for Bx becomes mu 0 I by 2 pi x Weber per meter square. Therefore, the flux through a cylindrical shell of radial thickness dx and axial length 1 meter is given by d phi is equal to bx into 1 into dx. Substituting for bx, we will be getting d phi as mu 0 I by 2 pi x dx Webers. Now the flux linkage per meter is equal to d phi, since the flux external to the conductor links all the current in the conductors only once. So d lambda is equal to mu 0 I by 2 pi x Weber terms. So the total flux linkage of the conductor from the surface to infinity, lambda external is equal to integral r to infinity mu 0 I by 2 pi x dx. That is equal to mu 0 I by 2 pi log x within the interval r to infinity Weber turns per meter. Total flux linkage due to one conductor. That is lambda is equal to total internal flux linkages plus total external flux linkage. So lambda is equal to lambda internal plus lambda external. Substituting for this lambda internal and external, will be getting total lambda. Lambda as mu 0 I by 2 pi into 1 by 4 plus integral r to infinity dx by x Weber turns per meter. So this is the internal as well as external flux. With this, we shall finish today's topic. We shall continue with the next session in the next class.